Darwin's son
George.
Charles Darwin's son George, was one of the people who pointed out eventually that nuclear energy could do the trick.
Oh,
nice little.
Okay, thank him for him. Yeah. Which of the Darwins explained tides for the first time?
Probably George. I'm not sure.
It was a Darwin, yes. And Newton and Galileo did not understand tides. It was, even though they had all the gravity necessary
Is that right?
to account for
yes.
it. There's a subtle point with tides where if you look at any textbook, it'll have like the moon.
Here, Neil deGrasse Tyson is talking about how you can possess the right law and still miss the phenomenon it creates. Gravity, by itself, tells you that masses attract. Tides require the next step. Not how strong gravity is, but how it changes from place to place. That change, the gradient, is the engine of the tides. If you stand at Earth's center, the moon's gravity pulls you a certain amount. On the near side, it pulls a little more. On the far side, a little less. Subtract the uniform pull that moves the entire Earth-Moon system around their common center of mass, and you're left with a stretching force. That's two bulges, not one. One facing the moon and one on the opposite side. Simple diagrams that show the moon tugging water toward it miss this crucial subtraction, which is why the word differential is the quiet hero of tidal physics. But water doesn't drape itself around Earth like a compliant blanket. Our planet spins, its oceans are corralled by continents, and seafloors sculpt the flow. The equilibrium bulges get dragged and distorted. Friction between water and the rotating Earth shifts the bulges slightly ahead of the moon. That misalignment matters. The moon pulls on the bulge, and the bulge pulls back, creating a torque that transfers angular momentum. Translation: the day gets longer, and the moon inches away. Laser beams bounced off retroreflectors left by Apollo astronauts measure it, about 3.8 centimeters a year. The sky looks still. The ledger of momentum proves it's not. Pause there and let that sink in. The moon, the most familiar object in our night sky, is slowly slipping from our grasp, not because gravity failed, but because it's doing exactly what gravity does in a rotating, dissipative system. This is where George Darwin, son of Charles, made his mark. He didn't have lasers, but he had the logic of tides. He reasoned that if friction is draining Earth's spin to the moon's orbit, then in the past, days were shorter and the moon was closer. Geological clocks confirm it. Ancient tidal rhythmites show more days in a year hundreds of millions of years ago. The Earth-Moon relationship is not a static arrangement. It's a slow negotiation governed by conservation laws, and that negotiation resonates across the solar system. Consider Jupiter's moon, Io. Its surface is a conveyor belt of volcanoes because Jupiter and neighboring moons pump tidal flexing into its interior. Europa's subsurface ocean stays liquid for the same reason. Saturn's moon, Enceladus, vents geysers into space, powered by tides that knead its icy shell. Wherever gravity has something to pull against, a spin, an orbit, an eccentricity, energy dissipates and worlds change. On planets orbiting small, cool stars, close enough to be warm, tides will likely lock one hemisphere into perpetual day and the other into perpetual night. If we ever ask, is there life there? The first reply may be, show me the tides. So why did brilliant thinkers before us struggle with tides? Because they tried to force a one-force, one-effect story onto a problem that lives in differences and frames. Galileo proposed sloshing from Earth's motion. Newton gave us the right force, but needed Laplace and later mathematicians to build the dynamic tide we measure in harbors, with amphidromic points and resonant bays like the Bay of Fundy. The moral is not that they were wrong, but that nature paid them only when they paid attention to gradients, geometry, and dissipation. The sun tells a parallel tale. For much of the 19th century, the best idea for the sun's power was gravitational contraction, the Kelvin-Helmholtz mechanism. Squeeze a massive ball of gas, heat it up, and radiate. It works, but only for tens of millions of years. Geologists and biologists were already reading a much older Earth in the rocks and fossils, and the numbers didn't match. The law of gravity sat on the table, but the phenomenon of a billion-year star demanded a new ingredient. Enter nuclear physics. Arthur Eddington proposed that the sun shines by fusing light elements into heavier ones, tapping EEMC2. Aston's precise measurements revealed that 4 hydrogen atoms weigh more than a helium atom by a tiny amount. The sun cashes in that difference as energy. Hans Bethe mapped the pathways, the proton-proton chain, and the CNO cycle. George Gamow showed how quantum tunneling lets the protons merge despite their mutual repulsion at solar core temperatures. Once again, the explanation lives in a difference: mass defect into light. Once again, the timescale transforms from millions to billions of years and pulls biology, geology, and astronomy into the same timeline. You can feel the through line here. Whether it's ocean tides or stellar furnaces, the big leap comes when we stop asking, "What is the force?" and start asking, "Where's the gradient? Where's the energy budget incomplete? Where's the frame of reference hiding a subtraction we forgot to do?" Those questions convert laws into understanding. They turn a general principle into a prediction you can test, a phenomenon you can measure, and, in some cases, a destiny you can forecast. So, the next time you stand at a shoreline and watch the tide creep over your shoes, see the silent math at work: a gradient drafting bulges, friction twisting them, and a moon that will be a little farther away by the time you dry your feet. And the next time you feel the warmth of sunlight on your face, remember that its origin is not firewood on a cosmic scale, but the subtle accounting of mass transforming into energy by the probabilities of quantum mechanics. The universe is not merely about forces. It's about differences, flows, and the ledgers they keep over deep time. When we train our minds to look for those differences, the world stops being a list of facts and becomes a system of causes. That is where understanding begins, and where wonder evolves into responsibility for what we know. Like if this was interesting, and hit the subscribe for more.